All right, so we're going to start the physics unit today, and what we're going to start with is energy. Because energy is what basically drives all physics. Okay? You can't have something move if there's no energy to get it going. Okay? In most cases, it takes energy to keep something moving. We're going to mostly look in this unit at mechanical energy, which has to do with position and movement of objects, but we will talk about all the other forms of energy just to kind of identify them, and that's what we're going to look at today, energy and energy conversions. Okay? Obviously, what we go over today is not on tomorrow's test. Okay? This is part of the physics unit, so don't worry about like cramming this stuff into your head for tomorrow. It's not on your biology test. Okay, so the picture that we have here on this page is of the Inuit blanket toss. Okay? It's mostly ceremonial these days, but in the distant past, it was an important part of their hunting procedures. In the high Arctic, the landscape is very much like Saskatchewan. You can see from one side of the province to the other. Okay? It's very flat. Right? And so that presents a problem if you're trying to hunt like caribou or something like that. It's very hard to sneak up on something if there's no cover. Okay? There's no trees, there's no hills, okay? Things like that. So your prey can see you coming from 30 kilometers away over the horizon, okay? And so it's very difficult to sneak up on them. So what they would do is they would try and get themselves a better view of the surroundings by putting the smallest member of the tribe on a blanket and then having everybody else grab the blanket and throw them up in the air as high as possible. Okay? That way it was like climbing a tree. You can't climb a tree in the Arctic because there aren't any, okay? At least in the part of the Arctic where the Inuit live. Right? So the only other option was just to throw people up in the air and catch them. That's key part two, catch them before they hit the ground, okay? So that they could see a little bit further. They could see over the horizon, okay? And that would allow them to kind of pinpoint where a herd would be, and then they could kind of work until they had surrounded them from all sides and then come in on them that way, okay? Now, the blanket toss, from a physics perspective, represents the use and conversion of several different kinds of energy, okay? Where does the energy come from to throw the person up in the air? You got all these people hanging onto the blanket. Where does the energy come from to throw that person in the air?
The other people.
From the other people. Okay, so the other people are pulling on the blanket. Okay, that represents work or mechanical energy being input to the blanket person system. Where did they get the energy to do that from? Where did the people get the energy to pull on the blanket from?
Like food.
From their food. Okay, where did their food get energy from?
The earth, like.
Yeah, from other organisms. If they were eating fish, the fish probably ate something else. Okay, eventually we would get to plants, and then eventually we would get to the sun. Okay, so what we got here, if we're like going right back to the very beginning, would be that the energy used to throw this person up in the air came from the sun. Okay, solar energy was converted into chemical energy by plants. Okay, the plants were eaten by animals. Okay, who converted that energy into their flesh, okay, their muscles and whatever else, and then the Inuit people would eat their flesh, and that would be converted into chemical energy in their body, which could then be used to convert into mechanical energy of movement of their arms and throw the person from the ground, where they would have no mechanical energy, into the air, where they would have more mechanical energy. Okay? And when they're here at the highest point, they have gravitational potential energy, because they're high above the ground, okay? And they have the potential to fall back down. Right? Now, in order to stop that person, do they have to do just as much work as when they threw them in the air? If they want them to not be injured, yes. Okay? They have to hold that blanket, catch them, and resist them falling into the blanket. All right? So all of that represents lots of different energy conversions that go on, and that's what we're going to look at today. It's basically types of energy and energy conversions. Okay, now, here's the thing about energy. It's really difficult to quantify or explain, because energy is not something you can hold in your hand. Energy isn't matter. Matter and energy are very different. I can hold matter in my hand. I'm doing it right now, holding air in my hand. Okay? I can do that. I can measure how much is there. I can take its mass, all of that stuff. But I can't hold energy in my hand. It isn't a material, so it behaves differently. Okay? And the problem with early studies of energy and early understanding of energy is people needed it to be something tangible. Okay? So they had all kinds of different ideas about how energy worked. It was this invisible fluid that flowed from one object to another when work was done. Or if you put a hot object next to a cold object, the energy would naturally flow from the hot to the cold. Okay? And we know that that's true. We just know it's not a magic liquid, okay, or magic fluid like they would say it was. Okay? It's not a material at all. Energy can do things that matter can't, simply because it isn't matter. Okay? Everyone kind of follow me there? All right. Now, okay, so, yeah, we talked about that paragraph. Okay, so we're going to talk about some of the different kinds of energy here, right? Chemical energy is one of the kinds of energy. We're talking about it first because, well, as much as we might want maybe for us to find alternate energy forms, chemical energy still drives pretty much everything. Okay? You probably drove to school in a car that used chemical energy, probably. And maybe some of you have an electric car, okay, or at least a hybrid electric car. Okay? But you probably still used chemical energy to get here, especially if you rode the bus. If you walked here, you still used chemical energy to get here. Okay? Most of our electricity is generated by chemical energy, burning coal or burning natural gas. Okay? Chemical energy is what essentially at this point drives the world. Okay? It's what makes everything happen. So chemical energy is potential energy. It is stored in the bonds of the fuel. Okay, so if we're looking at something very, very simple, okay, this is propane, C3H8. Okay, if I combine that with oxygen, what will happen? Think back to chemistry. That's the first half of what kind of chemical reaction? A combustion reaction. Okay? So chemical energy is generally released by combustion. Even the food you eat is essentially combusted in your body. Cellular respiration is really a combustion reaction that happens at a low rate. Okay? So when I burn propane in a barbecue or a furnace or something like that, what I'm really doing is breaking all of these chemical bonds. Every time I break one of those, the energy was stored in it is released. And it's released as thermal energy, which we sometimes call heat. Okay? That's what it's released as. And then that heat can go and do other things. For us, for generating electricity, for example, okay, it's used to turn water into steam. And then the steam turns a turbine that generates electricity. Okay? So all chemical energy is the energy stored in the bonds of the fuel molecule. Early studies of fuel and energy involved discovering that some fuels had more hidden secrets in them than others. That is, some fuels had more energy. If I burn a kilogram of coal versus a kilogram of propane, okay, I get different amounts of energy from each one. If I burn a kilogram of wood, I get way less energy than burning a kilogram of coal. Okay? Wood is not as energy rich as coal is. Okay? Everyone kind of follow me there? So that was kind of the introduction to fuels and the kind of chemical sciences of energy. Okay, all right, so chemical energy, and this you'll probably want to underline or highlight or do something with. Okay, chemical energy is the potential energy stored in the chemical bonds of compounds. Okay, prime example, the food you eat contains chemical energy that your body uses to do work in your cells. Okay, now why is chemical energy considered to be a type of potential energy? Why is a tank of gasoline dangerous? It could explode, right? It could catch fire. But it isn't dangerous until that happens. Okay? That's why we call it potential energy. It has the potential to release that energy, but it doesn't until something happens to it. Okay? So chemical energy is a form of potential energy because it's energy that is stored in that particular material. Okay? Kinetic energy, on the other hand, if you had a giant boulder rolling towards you, okay, that energy is right there. There's nothing potential about that. It's rolling towards you. It's got the ability to do work. Okay, so that's kind of the difference. All right, electrical energy and magnetism. So electrical energy is the kinetic energy stored, or sorry, not stored, the kinetic energy of moving charges. That is electrons flowing from one place to another. Right? So when you hook up something to a battery and turn it on, electrons flow out of the positive side of the battery and back to the negative side of the battery. Okay? Sorry. I don't remember which way it goes. Either way. Okay? So the electrons flow out one end, they go back to the other. Okay? If I put something in their way, their energy, that is their desire to want to go from one pole to the other, okay, can be used to do work. So those little tiny electrons, okay, can be harnessed to do stuff as they go past. Right? If, for example, we had an old filament-style light bulb, like the old Thomas Edison, right, kind of light bulb that has the filament inside, like that, okay? Those glow because the little metal filament inside is made of tungsten, which is a very poor conductor. So the electrons are moving really, really fast, and then they hit the tungsten and they slow down. Okay? And when you slow something down, it loses energy. That energy becomes heat inside the filament, and the filament glows bright white, okay, and provides the light that we associate with a light bulb. Okay? Everyone okay with that? All right, so if it was an electric motor, okay, then the electrons would be going past these magnets and causing the magnets to exert force, which would cause the electric motor to turn. Right? So what we're doing is we're harnessing the energy of billions upon billions of tiny little electrons that are moving through a wire. Okay? That's what electrical energy is. Okay, so electrical energy is the work done by moving charges. Can chemical energy be turned into electrical energy? We only talked about burning chemical energy, but can you turn chemical energy into electricity? Absolutely you can. That's how a battery works. Okay? A battery uses chemicals that have electrical potential, okay, and they can allow a current to flow. Okay? So any type of battery, be it like an alkaline battery or a lithium-ion battery that powers your phone, okay, all of those use chemical energy. Some of them, the reaction is reversible. So the lithium-ion battery that powers your phone can be recharged over and over and over again. Okay? All you do is make the electrons go back the other way. Okay? Can you do that with a regular battery? You can't. Okay? That's why, actually, you can do the drop test on a battery to figure out whether it's still good or not. How many people have ever done the drop test on a battery? Okay? You take just the battery and you hold it, you know, about this far off of a table, and you drop it. Okay? If it stands up, it's still good. If it tips over, it's dead. Okay? Because what happens is the electrons always go the same way. Okay? So what happens is the electrons start to go from one end to the other. They start to build up in one end. One end gets heavier than the other as you deaden the battery or as you use it up. Okay? And so mass collects in one end, so when you drop it, it tips over. Okay, if it's still good, the weight is at the bottom. So when you drop it, it stays upright. Okay. All right, so that's how batteries work. This picture here, this is the Volta pile. It is the great-great-great-great-great-great-grandfather of the modern alkaline AA battery. Okay, it was about that big around and about that tall, okay, so it wasn't super practical. Okay, but it did provide evidence that you could convert chemical energy into electrical energy, and that electrical energy was the result of moving charges. Okay, that Volta pile, that's an important one, okay, provided a constant electric current and was invented by Alessandro Volta, whose contributions were so important that the units for charge are named after him. Volts. Okay, now, magnetism and electricity are very closely related. Okay, and in fact, one can cause or produce the other. So, a guy named Ørsted was showing that you can actually cause a magnetic field with a current carrying wire. Okay, so what he did is he had a wire that was carrying a fairly strong current, okay, just kind of running over top of a table, and he took a compass and he moved the compass underneath it. Okay? And as soon as the compass got underneath the wire, it went from pointing north to pointing along the wire. Why would that happen?
Because it has a greater electric charge.
Okay, partially, the charges are producing magnetic effects. Okay? Around a current carrying wire, you get a magnetic field, very similar to the Earth's magnetic field. Okay? If we're looking at Earth, okay, so this being the North Pole and this being the South Pole, Earth has a magnetic field that looks something like this. Okay? And there's lines of force that go along that magnetic field. If you hold the compass out, it will align with those lines of force and point north. Okay? Now, those lines of force are quite weak because they're produced from, well, I should say weak, but they're weak enough, okay? Because they're produced in the core of the Earth. If I have any other thing that produces a magnetic field anywhere close to that, the compass is going to respond to it. If I grab even a small magnet and move it anywhere close to the compass will start going towards it because its field strength is closer and thus stronger. Okay? If I have a current carrying wire, the same thing can happen. It will produce a magnetic field around it, and the compass will orient with that magnetic field parallel to the wire. Okay? The same thing can happen if you get interference on your phone. Okay, or you guys might be too young to remember this, but back when Wi-Fi was kind of younger in its infancy, you could scramble Wi-Fi by firing up the microwave. Okay, it can still work with Bluetooth. If you've ever, you're down in the kitchen, you're listening to something on your Bluetooth headphones, you fire up the microwave and they cut out. Okay, it's because the microwave produces a magnetic field when you fire it up. Okay, and that magnetic field will interfere with the magnetic field of the transmitter and receiver, okay, for lots of things. Old Wi-Fi, Bluetooth, okay, all of that kind of stuff. Sort of make sense? Okay. So all of those things produce magnetic fields. Now, here's the thing about both electric and magnetic fields that everyone needs to know. Their effects decrease exponentially with distance. Okay? That means if I'm standing right next to the source of a magnetic field, its effects are going to be very strong. If I move twice as far away, its effects are 4 times less. If I move 3 times further away, its effects are 9 times less. If I move 4 times as far away, 16 times less, and so on and so on. Okay? So this is what kind of pokes a hole in this argument. I don't know if you guys have ever heard this, but I don't want to live near a cell phone tower because it'll cause brain cancer. Okay? Or I don't want to live under these high voltage wires because they'll cause brain cancer. Okay? There's this whole idea that all of these things cause cancerous tumors. Okay? If you talk on your phone, that's a magnetic field close to your brain. Okay? If you live next to a cell tower, that's not a magnetic field close to your brain. Okay? Unless you sit on the transmitter all the time, you are perfectly safe. Okay? I only say that because we were supposed to get a transmitter right out there, a cell tower, right there, because you know how crappy the cell reception is here. Okay, walk around the school and get dropped calls. Okay, but we were supposed to get one there, but a group of people put up a stink because they said it would be bad for you. Okay, I only remember that because our principal at the time came and she's like, all these people are putting up a stink about this cell phone tower that we were going to get put in this area. Is this realistic? And Mr. Dickey and myself sat down and went, here's the math of it. That is stupid. Okay, here's the math of it. Unless you're standing on top of the damn thing all the time, you're perfectly safe. But some people just can't be convinced. And they ended up not putting the cell tower in. Because, well, it's only the people who make noise who get heard. That's a terrible life lesson. But it's true. The squeaky wheel gets the grease. All right, so Oersted discovered that electric fields produce magnetic effects. This was kind of the ancestor of the radio transmitter. Okay? This idea that an electric current can produce a magnetic effect is what eventually led to the development of radio. Okay? Another scientist named Faraday, okay, he discovered that magnetic fields can produce electric effects, that is, electric currents. What he did is he had a voltmeter, okay, something that measures electric current, okay, and he had a coil of copper wire. He took a bar magnet and pushed it through the coil of wire, and all of a sudden there was a current. And if he pulled the magnet out of the coil, the current went the other way. Pushed it in, the current went one way. If he pulled it out, it went the other way. Okay? So what he discovered was that a magnetic field can push electrons. Electrons are kind of repelled by a magnetic field. Okay? So he discovered a way to generate electricity. Okay? Alternating current, right? AC, right? Alternating current. You get a magnet going back and forth inside a coil of wire, okay? You get alternating current. Okay? The magnetic field produces, okay, this push and pull of electrons. Okay? All right, so know those guys. Oersted, okay, he would be electricity and magnetic effects. Okay, and Faraday, first electric generator. Magnets produce electric effects. Okay, would you say that electricity has been an important development in human civilization? It's been, yeah, like game changing, really. Okay, society changing to have electric power. So once it was discovered, people wanted to find better and better ways to generate it, or different ways to generate it, or use it, and things like that. So that's kind of Oersted and Faraday here. But also, another person named Seebeck. Seebeck invented a way to turn heat into electricity. Okay? He took Oersted's idea that you can detect a magnetic field with a compass. Okay? And what he wanted to do was show that he could generate an electric current with just thermal energy, with just heat. Okay? So what he did is he set up this device here. He had an iron bar on the bottom, a compass needle, and a copper bar. Okay, sitting on top. Now, iron and copper transmit heat or conduct heat at very different rates. Okay, copper conducts heat very, very quickly, very, very easily. It also conducts electricity very, very easily. Okay, iron, on the other hand, is much slower at both. So what he did is he started heating up the iron bar with a candle. Okay? And the different rates at which the heat could travel through resulted in a flow of electrons, or an electric current, which was detected by the compass needle, which started at this angle, and then after a short amount of heating, went parallel to the copper bar, okay? Showing that this is the direction the magnetic field and thus the electric current are traveling. Okay? This is the first thermocouple. Okay? Thermocouples are used in a lot of things today. Okay? They didn't get a lot of use up until more recently, we'll say. One of the things they do is they're used as a circuit breaker. How many of you have ever popped a circuit breaker in their house before? Maybe I had to go downstairs and flick the switch, okay, because you plug too many things in one outlet, okay, and breaker. Those are a thermocouple. They break open the circuit when the circuit gets too hot. That's what prevents an electric fire in your house. Okay? So you've got this wire that's running into your breaker box. Okay? If you're running a lot of current through it, it'll get hot and it'll generate enough electricity for a little electric switch to pop. Okay? That breaks and opens the circuit, and now no electricity can go through until it's cooled off. If you try and reset the breaker before it's cooled off, it'll just pop again. Okay? So you have to wait long enough for that heat to go away, and it's a very important safety feature that we use to prevent electric fires. Right? The other place thermocouples get used is in hybrid and all-electric vehicles. They build them into the brakes. When you apply your brakes, do they get hot? Yeah, you've got metal on metal. That's how you stop your car. Yeah, you squeeze two pieces of metal together, okay, and it stops your car. Well, that generates an incredibly large amount of heat. Well, it wasn't very long after the idea of having a hybrid car using an electric battery to power itself that people thought, you know what? We could use some of the energy to charge the battery. Okay? And so now what we have is thermocouples built into the brake rotors of hybrid and all-electric cars. So when you apply the brakes, a current gets generated from the heat and goes back and charges the battery. So a bunch of the energy you use to build up speed can get returned to the battery through what we call regenerative braking. Okay? We recently, back in November, got a plug-in hybrid vehicle. And now I play games with it. It actually has a little thing called a brake coach, which tells me how well I've done with my regenerative braking. Okay? It gives me a score as a percentage. If I just slam on the brakes and stop really fast, okay, I get like 30% of the energy returned. But if I brake nice and slow and coast to a stop really slowly, I get 100%. So every time I drive that car, I'm always aiming for 100% on my regenerative braking, because I can charge the battery a little bit by just recycling the energy I use to accelerate. Okay? It's actually pretty smart to use that as a way to regenerate that electricity. Okay, so that's another one of the things that thermocouple can be used for. I am not looking forward to the first time I have to replace the brake rotors in that car. I imagine they're quite a bit more expensive than ones without thermocouples. But that's for another time. Okay, questions on what Seebeck did? Okay, so Seebeck was thermal energy to electric energy. Now, here's the thing about this, though. It's not very efficient. Okay? A thermocouple does not generate a large amount of electricity. Okay? Which is why we don't use it to generate large amounts of electricity. It's nice to have it to, get some energy back in your battery in a hybrid car, but we wouldn't start a fire and put a thermocouple over it to power our house. Okay? It's not that efficient, so we don't use it for that. Okay. All right, nuclear and solar energy. We talked a little bit about nuclear energy back in the chemistry unit. In the nucleus of an atom, there is potential energy. Okay? If I change the nucleus of an atom, that energy will be released. And there are two ways to change the nucleus of an atom. Break it, or force it together with another one. What are those two processes called? They both start with F.
Fusion and fission.
Fusion and fission. Okay? Nuclear fission is the breaking of electrons. This is what we typically do with nuclear energy. Okay, so we break the atoms up, and lots of thermal energy is released when we break them. That thermal energy is used to evaporate water into steam, and steam turns a turbine. Okay? Fusion, on the other hand, is when you force two atoms together to make a larger atom. Okay? Just this past fall, they had the first instance of a fusion reaction that actually produced as much energy as was required to cause it. This has always been the barrier to nuclear fusion. In order to make it happen, you have to use so much energy that it's cost prohibitive, basically. Okay? You have to put more energy in than you get out with current technology. Okay? But back in the fall, they had the first fusion reaction that actually broke even. So now what they're hoping to do is move forward and get towards that ever elusive cold fusion, okay, where we can just get energy, basically do nothing, and it would be free. Okay? So we're kind of moving towards that. Now, this is what powers the sun. Okay? Nuclear fusion is the source of energy for the sun. Now, the energy that causes that fusion to happen is from gravity. The sun is huge, okay? Like beyond huge, unfathomably big. Okay? And it's got a lot of mass. And the more mass you have, the more gravitational pull you can exert. There is so much gravity on the sun that it crushes hydrogen atoms together to form helium atoms. Okay? That's nuclear fusion. That happens all the time on the sun, and that's what gives us the energy we get from the sun, is the hydrogen fusion reaction, okay, that goes on there. Okay? Now, we didn't always know that. Okay? For a very long time, people thought when they looked up at the sun, they went, ooh, that's bright. It looks like a big fire. And so they actually figured it was a big fire in space. Okay? What's wrong with the idea of having like a chemical fire in space?
There's no oxygen.
There's no oxygen, yeah. Okay? And the other part of it is, if there was actually a chemical fire in space, and the sun was actually a chemical fire, like a campfire, it would have burned out after 5,000 years. Would have used up all of its fuel. Okay? So that wouldn't work. Okay? What we discovered later is that it's not a chemical fire. It's a nuclear fire. It is a big fire. If you've ever seen videos and pictures of the sun, it's a big fire, but it's a big nuclear fire. All right, so nuclear energy then. Okay? Nuclear energy is the potential energy stored in the nucleus of an atom, and when the nucleus of an atom is split by fission, or the nuclei of two atoms combine, fusion, that energy is released. Okay. Does the sun put out lots of different kinds of energy as a result of this? Yeah. It's not just heat, it's also light. Heat is a form of light, but okay. We get all kinds of different light energy from the sun as well, and that's little traveling light particles called photons. That's what solar panels use to make electricity, because photons hit solar panels at what speed? Photons come from the sun. Photons are light particles. What speed do photons move at? Speed of light. Is that fast? Okay. So even though photons are basically massless, they have an incredible speed, which means they have a lot of energy. So when they smash into a solar panel, it can generate electricity. Okay? That's how a solar panel works. It takes the kinetic energy of these moving light particles and converts it into electricity. All right. All right, motion and energy, that's the stuff we're going to be most focused on here. How many people have seen Newton's cradle before? Okay. You take one ball and you let it go and go tick, 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 back and forth. Okay. Believe it or not, this almost got Newton beheaded. Okay. Because when he first invented it, there was a lot of, let's say, animosity between the scientific community and the church. Okay. There are much better terms now. Okay. But at that time, this did not go over well. Okay. Because Newton pulled that one ball away and let it go, and the ball on the other side flew up in the air. Okay? And right away, people looked at him and went, oh, you're a witch. because that was the thinking at the time, right? That's magic. You're a witch. What do we do to witches? We burn them. Okay, yeah, so it didn't go well. It didn't go well for Newton. And he had to really do a lot of explaining to go, look, this is not witchcraft. This is not magic. There's this living force that exists within me that I give. And they're like, that sounds like witchcraft. And then, so he had to kind of back up a little bit, okay, and explain that, no, there's this stuff. He didn't use the term energy. That term wasn't around as much, okay? And so he talked about how this ball can hit another one and transfer stuff to it, and that transfers through to the ball in the end and makes it go up. It's not magic. It's the transfer of this living force from one thing to another, okay? And which later became known as mechanical energy, which is kinetic and potential. By pulling this ball away, he did work, gave it gravitational potential energy. When he let it go, the gravitational potential energy turned into kinetic. And kinetic energy can be passed from one mass to another. So it would pass through all of the masses and make the mass on the far end, which had no resistance to its movement, fly up in the air. Okay? So very, very simple demonstration of energy being converted and transferred. Okay? All right. So this was the idea. Okay? Here, anything that's in motion can do work because it has kinetic energy. So wind. Okay? That's why wind can damage things. Flowing water. That's why we build hydroelectric dams. Right? We're harnessing the kinetic energy of these moving objects. And the other type is gravitational potential energy. If you lift something above the surface of the earth, it could fall. Okay? So gravitational potential energy is just that. It is potential. It can't do any work until it gets converted into what kind? Starts with K. Kinetic. Right? Because if you drop something, it starts to speed up. Okay? It converts its gravitational potential energy into kinetic energy. Okay? Now, let me ask you this. This cup, does it have energy right now? What kind? Potential. Potential. Gravitational potential energy, because it could fall. Let's say, just picking a random number, it has 10 joules of gravitational potential energy. If I drop it, how much kinetic energy will it have the instant it hits the ground? So I'm holding it right now, it's got 10 joules of gravitational potential energy. If I drop it, just before it makes contact with the ground, how much kinetic energy will it have? You're all thinking it, but you think I'm trying to trick you and I'm not.
10 joules.
10 joules. Okay? Because there wasn't any way for it to get any more. Okay? The only reason it has 10 joules of gravitational potential energy is because I picked it up and lifted it to here. How much work did I do? 10 joules, yeah, okay? In the perfect physical world, to get it here, I have to do 10 joules worth of work. Now it has 10 joules worth of gravitational potential energy. When it falls, it'll convert that into 10 joules of kinetic energy. Okay? Everyone okay with that? So that's the idea behind like a hydroelectric dam. If you get water backed up behind a dam, you get it to go higher and higher. You give it gravitational potential energy. Then you let it fall over the dam. Well, instead of just falling and converting all of its gravitational potential energy into kinetic, you make it turn a turbine on the way down. And that turbine steals some of the energy, and that energy gets turned into electricity. Right? So water that comes out of a dam isn't going as fast as water that would have just fallen that far, because some of its energy got used to do work along the way and make electricity. That sort of makes sense? Okay, now the other thing we need to know here is that an object can have both potential and kinetic energy at the same time. And that total is its mechanical energy. heat and energy. Now, heat is a poor word for this. Because probably up until now, you've been told heat is a form of energy, and we use the term heat interchangeably with what is actually what we mean. Okay? Heat is actually thermal energy. Okay? When we say heat, we usually mean thermal energy. Okay? Heat is actually a transfer of thermal energy. Okay? That's why we say if I get, come up to a campfire, you say, I feel the heat coming off of this fire. Well, yes, you do. You feel the thermal energy being transferred from the fire to you. That's what heat is. Heat's the transfer of thermal energy. But we often refer to thermal energy as heat, okay, when that's not technically true. Okay? Unless I feel thermal energy coming from something, I don't feel the heat. Okay? So they're not quite the same thing, right? For example, an ice cube has thermal energy, but it doesn't feel hot when I put it in my hand because it has less thermal energy than my hand. So the heat flows from my hand to the ice cube. Okay? The ice cube would say, ooh, this hand is hot. Okay, I feel the heat coming off of this hand. I feel, and we look at the ice cube and it's like, I feel the cold coming off of this. Well, we actually feel the loss of thermal energy. You can't transfer coldness. Okay? You can only take heat away. Okay, so the Greeks had this idea that, the atoms, the tiny particles, all of that stuff. Okay, Joseph Black, who was a Scottish physician, he observed, and this is like, mind-bending. He observed that when a cold object is placed in a cup of hot water, it gets hotter. Crazy, right? Okay, but he discovered that that was true no matter what the objects were. That energy only ever flowed from hot to cold and never the other way. Okay? The cold object never got colder and the hot object hotter as a result. Okay? Energy always flows from hot to cold. And that became known as thermodynamics. Okay? This flow of energy. Okay? Thermo means energy, dynamics means change. So this is the changing of energy or the flow of heat. Okay? Now, he thought that this was the fluid thing that I talked about at the beginning. He thought that heat was this caloric fluid that flows naturally from hot things to cold things, okay? But obviously we know now it's not a fluid, okay? It's energy. Okay, so we'll say Joseph Black, thermodynamics, that was his. Okay, and this sentence at the bottom we already kind of wrote down, okay? But the transfer of thermal energy from a hot object to a cold object is heat. Okay. Everybody rub their hands together. Getting hot? Why? Friction, okay? Friction's a force. It's there. It's the reason why heat is coming from your hands. But what kind of energy is working against that friction? My hands are moving. What kind of energy is there if things are moving? Kinetic. Or even more accurately, mechanical energy. Okay? Mechanical energy almost always produces heat. Because as soon as something's moving, it's moving against something else or through something else. Okay? And that's going to produce friction. Anytime two surfaces slide past each other, there's going to be friction. Okay? And that's going to produce heat. Okay? Now, this guy here, Benjamin Thompson, okay, who later changed his name to Count Rumford, which seemed like a bad move to me, but whatever. Okay? He moved to Bavaria, which was part of Germany, and became the Minister of War. His job was to supervise the production of cannons. Now, you make cannons by having a big lump of metal and boring it out with a big drill. Okay, now, this is back, way back, okay, so 1800. We don't have, electric drills or anything like that. We have people turning a mechanical bit, okay? Basically augering out a big lump of metal, okay? So you've got metal on metal, and you're trying to drill out a hole in this big lump of metal. Is that gonna make a lot of heat? That metal's gonna get pretty hot, right? Okay, well, this was the discovery that mechanical energy was related to heat, that mechanical energy could turn into or produce heat, okay? Because what Rumford observed was that his workers would take coffee breaks, actually tea breaks, after a while, because they would put a teapot or a kettle on top of the cannon, and while they were boring it out, enough heat would be produced to boil the water. Okay? Once they got the water to boil, they could take a break and have a cup of tea, and then they could go back to work again. Okay? And he was wondering where that energy was coming from. Okay? It's just like, why is this cannon getting hot? Well, there's friction between the metal bit and the piece of metal that I'm making a cannon out of. Okay? Where's the energy to turn the bit coming from? It's coming from the people. Okay? Where's the energy in the people coming from? From the food they ate. He was making these connections between these energy transfers. All right? So he suggested that heat could be manufactured from mechanical energy. Okay? He was the first to realize that heat and mechanical energy were related. Okay? And once he realized that, people started to make the link, namely Thomas Young, okay, made the link between mechanical energy and this idea of kinetic and potential energy in moving objects. Okay? From there, we got our current definition of energy. Energy is the capacity or ability to do work. Then what's work? Energy is the ability to do work. You can't do work without energy. So what's work? How much energy does the cup have right now? None. It's on the ground. Okay? It can't fall any further, and it isn't moving. So it has no mechanical energy. It's got energy now? Why?
Because it could fall off the desk.
Okay, it could fall off the desk. Why couldn't it fall off the desk?
It's on the edge.
Okay, it's on the edge. How did it get there?
Put it
I put it there. What did I do to put it there?
or
Work. Exactly. That was a lot of work. Okay? Work is a transfer of mechanical energy. That's why you have to have energy to do work. Okay? Energy is the ability to do work, because work is a transfer of energy. So if I want to do work, I've got to have energy to give away. Right? So a lot of people say, well, that's kind of a chicken and the egg thing, isn't it? You can't have one without the other. Which comes first? Well, first off, chicken and the egg argument is stupid. Everybody knows which came first. Which came first? Eggs. Eggs came first. You want to know why? Birds, chickens are birds. Birds evolved from reptiles. Reptiles lay eggs. Eggs before chickens. Now that we've settled that argument, this is no longer a chicken and egg argument. Okay? This is a relationship called the work energy theorem. Okay? Work is a transfer of energy. Energy is the ability to do work. Yeah, they are dependent on each other. If I don't have energy, I can't do work. Okay? I can't transfer or give away what I don't have. Okay? That's why we're not afraid of a piano sitting on the ground. But we would be naturally afraid of one suspended from a crane over our head. Okay? We understand that that piano has the ability to do work. It could change our shape in an undesirable way. Okay? But the piano on the ground is much less scary. Okay? All right. That comes cup has been more useful today than it has been in the year it's been sitting there. Okay. Now, last guy we got to talk about, Joule. Okay. He's really important because the units for energy are named after him. Okay. Always a good sign. If you've done something right in the scientific world, they'll name a unit after you. Okay. The units for force are named newtons. The units for energy are named joules, so those two people are pretty important. Okay? Now, what Joule did is he showed that mechanical energy was a form of energy by turning it into heat, okay, and like actually measuring it, okay, and showing that I did this. This resulted in this many joules of energy, and when I let it go, all that energy turned into this. Okay? So we had these experiments. Okay? These are Joule's experiments. This one's kind of less important. This one here, the falling block experiment, that's kind of the big one. All right? So he had a stationary block and he had this falling block. In the stationary block, he had a thermometer. Okay? Just drill the hole, put the thermometer in the stationary block. Then he lifted the other block up and away on a pivot, and they let it go. When the falling block smashed into the stationary block, the block's temperature went up. And people understood that heat was a form of energy. It was thermal energy. They understood that. It was something they had experience with. Okay? But understanding that potential energy was a form of energy was something they couldn't as easily understand because they couldn't feel it or see it. Okay? I mean, they understood the piano example I just gave you, okay? But they didn't understand so much why. Okay? This was the proof that something perched above the Earth's surface that could fall possessed the ability to do work because they showed that its energy could be converted into other forms. Okay? You could repeat an experiment like this at home. If you take a hammer and a piece of wood, okay, and just pound that piece of wood a couple of times with the hammer and then put your thumb where you were hitting, it'd be hot. Okay? And that's just the result of you taking mechanical energy, and as soon as that thing stops, the energy's got to turn into something. It turns into sound, and it turns into thermal energy, it turns into heat. The block gets warm. Okay? All right. Okay. I would like you guys to answer these questions here. Okay, so 2, 3, 4, 6, 9, 10. Okay, so we'll get started on those. That'll probably take us to the end of class. Okay, the answers are all in the notes there.